Chapter number 9 covers water sources, the hydrologic cycle, soil water budget concepts, groundwater, and our water supply. Water is such a temperamental thing. It's essentially a non-renewable resource. Once we ruin it or do something to it, it's hard to get back. And we have very little water to utilize amongst the 7+ billion people on the surface of the earth. But 97% of it is in the oceans. 86% of all evaporation is from the ocean sources. So when we start to look at some of these numbers here, very little can be utilized by 7+ billion people. Looking at this number here, this little area up here is all the water that we can utilize, because we have something called desalination, but we don't have large-scale desalination abilities to take the salt from the water. It's very costly and expensive. But of all the water that we have, a good percentage of it's locked up in glaciers. So there's not much we can do with it, transport or whatever here. So what we deal with are rivers, deep groundwater, shallow groundwaters, freshwater lakes, saline lakes, which we can't utilize, stream channels. So what we're trying to utilize is this much water for 7 billion people. So we have surface water, rivers and streams, what we call runoff, and then we have infiltration and percolation. And basically, when water hits the ground, what does it do? And a lot of times when we start to build cities and we build impermeable surfaces, in addition to changing the temperature dynamics with respect to albedo, we've turned a permeable surface into an impermeable surface, which increases runoff. So there's some different dynamics that we do when we build water, when we build cities and whatnot. You can see the hydrologic cycle. I think I've shown this before. Precipitation and the percentages of these. We have a terrestrial lake, natural storage reservoir used for recreation. Where do they occur? Basically places where water won't percolate any further down into the ground. So we have our soil water budget, factors that balance. Previous classes I had where people went and kind of played with these. I don't do this too much in our class. This is one of my pictures this is Crater Lake, Oregon, out in the western United States. This is actually a caldera, so it's a volcano that basically collapsed on itself and filled in with water. This is the deepest lake in the United States. I think it's about 1,900 feet deep and about 6 miles across. So this thing, it's pretty neat, but it's created an equilibrium because I think it erupted about 8,000 years ago. It was really big, much bigger than Mount St. Helens from what we know. If anyone remembers that from 1980. But we have an equilibrium now where the rainfall going down equals the evaporation going up, because this is at about 6,000 or 7,000 feet in elevation, so there's not a lot of water sources, rivers that go into this, especially since it was a volcano. So how do we measure water? Measuring infiltration, percolation, we've got rain gauges, lysimeters and whatnot, soil moisture, wilting point where the remaining soil in the body is unavailable to point to plants. We've got field capacity. So you can see all the dynamics that go into having plants, and more importantly, plants that can be utilized by people. We have something here called the water table. If you've got a well, basically you have tapped into the water table right there. Okay, and hopefully in times of drought, this water table is going to get lower and lower. I have a well myself, and always worried about that. Now we have something called the drainage basin. So when an area hits a particular point in that, where does it empty out? So the Mississippi River. Okay. So the length of it's about 4,000 miles or so. We've got a big drainage area, about 3 million kilometers squared. It's about a third the size of the United States or so. So if a drop of water hits Pittsburgh, Pennsylvania, or Minneapolis, Minnesota, or Billings, Montana, it is going to empty through the Mississippi River right through downtown New Orleans. So the things that we do in Minneapolis or Pittsburgh or Billings are going to have a direct impact on the rest of the United States. So we can see the drainage basins for some of these, the discharge. You can see the Amazon has a lot of discharge because, well, essentially it's emptying a rainforest. It's down at the equator. So you can see the average precipitation, and you can see the Mississippi River right here, and this is the drainage basin here for the Mississippi River, about a third the size of the United States. You know, we have something here called the Continental Divide. If you ever drive over the Appalachian Mountains, you might see a sign that says you're crossing the Continental Divide, because everything here in Virginia empties out through the Chesapeake, whether it's the James River or the Petey River here, the Cape Fear River here in the eastern part of the United States. But anything on the other side of the Appalachians will eventually go through the Ohio or the Tennessee or the Arkansas River and right through downtown New Orleans. So it's important what we do to water. We have streams, we have runoff, zones of runoff, surface reservoirs, dams. So good quality cover the ground of surface reduces runoff. If we have a lot of plants, we are going to have less runoff, basically erosion. If we get rid of plants and vegetation, well, that area of land is not going to need as much water, and we're going to have more runoff. Okay, more basically junk, dirty water or whatnot. So there's a delicate balance between, if we clear cut or whatnot, well, that's going to increase runoff and do a lot of other things to that particular area, in addition to the actual oxygen supply. So we've got stream flow. You can see stream flow in urbanized areas because, like I talked about before, if you put impermeable surfaces, sidewalks, parking lots, or whatever, well, it can't percolate into the ground and eventually go to some subground water source or subsurface source out to a river or lake. It flows across the surface of the earth. Okay, and eventually gets into a sewer system or whatever. So this lag time is a lot less. This talks about groundwater resources, and then this relationship between mankind and our environmental resources. We've got point source and non-point source pollutions. Non-point source like farms, point source like smokestacks or whatever, that put junk into the atmosphere and degrade the water, and in this case the water and the air. Okay, we have aquifers underneath the ground. We have porosity. And then you can just see, a profile of artesian wells or whatnot. And then how do we utilize groundwater and the pollution? So point source accounts for about 35% of pollution, non-point source about 65%. Non-point source, basically you can't pinpoint where exactly it is. And then we have topographic changes that kind of change, that are changing. So when we take water out from the ground, we are basically taking out the support for what we call the pore space. Okay, so if we have water, we can build things on top of it. We take the water out, or we're going to have something called subsidence or subsidence. And so we might have uplifting or subsidence here. You can see an example here in California. And then the dynamics attached with gravity, water, and landslides or whatever. And then some of the things we need to consider. United States, high consumers of water and resources, energy resources in general. But, especially in the West with mining, grazing, transportation, we have something called fracking, which is occurring everywhere. And then we have dams, the Grand Coulee Dam. What do dams in the West do? Well, they help create energy. But what have they done to the surrounding area? What have they done to the wildlife? Okay, and these are some of the major dams in the Pacific Northwest. I used to live up here This is a big one here called the Dvorak Dam, and then we have, this is the Snake River here, and eventually out to the Columbia River that serves at the border between Washington and Oregon. And then you can see the Columbia River here. So we've got the Grand Coulee Dam, and then we have some all the way up into Canada. So this is the Grand Coulee Dam, one of the largest projects. I think this is a WPA project back in the 30s and 40s. And then it creates a lot of hydropower. So there's a lot of rainwater in these particular locations, and that means surface water, which means dams.